this lesson we'll be discussing the performance metrics for power, refrigeration, and a heat pump cycle. We're going to start with the power cycle, which we describe with the thermal efficiency, which we use for the symbol eta sub th. So when we're describing performance of cycles, we often look at something called desired over required. What is desired energy transfer with respect to what the required energy transfer for the cycle to occur is? So in this case, our desired energy transfer is going to be our work net. We want to produce work or power coming out of our system. We require heat transfer coming from our high reservoir. We can rewrite this in terms of rate of time or per unit mass. It's still going to be the same relationship of our network over the rate of transfer, or the heat transfer from the high reservoir. Now, if you remember that for cycles, our heat transfer is going to equal our network. Well, because of that, we can substitute this sum of heat transfers in for our network, and we can rewrite our thermal efficiency just in terms of heat transfer rates. This can also be written as 1 plus the heat transfer associated with the low reservoir divided by the heat transfer associated with the high reservoir. Now, if we think about this in terms, what are the possible extreme values we could get for this? To see our limitations for our thermal efficiency. Well, for our low reservoir, if we could possibly, the max we could probably get would be to get from the high reservoir if they were the same magnitude. Well, if our low reservoir heat transfer rate is the same as our high, well, remember that the low is going to be negative. So you'd have a negative, the same magnitude, so it would be a negative 1. So 1 minus 1, so we would have one extreme value would be 0. So this would be the case where all the heat transfer from the high reservoir went to the low reservoir. If that's the case, you're not producing any work or power, which means you have a horrible power cycle because it's not doing anything, which makes sense because you then have an efficiency of 0. The other extreme is, what if none of the heat transfer went to the low cycle? If that were the case, then that would mean all of your heat transfer from your high cycle were going to your work, net work. If that's the case, then you would have 0 over your heat transfer from high. 1 plus 0 is 1, so your max would be 1. So those are your ranges. You can have 0, you can have a basically non-existent power cycle. You can't reach 1 because efficiency of 1, because that would mean that you would have no reversibilities. So for a real cycle, it must be less than 1. Coefficient performance is what we use to describe the performance of both refrigeration and heat pump cycles. We'll start with the refrigeration cycle. So remember, for the refrigeration cycle, we have our desired over required. Our desired is that heat transfer coming from our low temperature reservoir. The required is work in. Now we put a negative out front here because remember, work in is negative, and our work is definitely coming into the system for a refrigeration cycle, so this is going to be a negative value. So we want to get a positive coefficient performance, so we put a negative in front to cancel that out. We can again rewrite this in terms of rates of time or per unit mass. And if we substitute in for our net work the sum of the heat transfers, and then we divide by our heat transfer rate associated with the low reservoir, what you get is a negative 1 divided by heat transfer rate high divided by heat transfer rate low plus 1. This is another way of doing your coefficient performance for refrigeration. The limitation for coefficient performance of refrigeration is that it must be greater than or equal to 0, the lowest value you can get. If we look at the heat pump, our desired is that heat transfer going to the associated with the high reservoir. It's heat out, so it's a negative, so it's a negative over a negative, so they cancel out, so that's going to be positive on its own. We can also rewrite this in terms of rate of time or per unit mass, just like the other ones. And if we substitute in the sum of the heat transfers for the work net, what you get is heat transfer rate high over the summation of heat transfer rate high and the heat transfer rate low. If we divide everything by the heat transfer rate associated with the high, the hot thermal reservoir, what you get is 1 divided by 1 plus the heat transfer rate from the low reservoir divided by the heat transfer rate from the high reservoir. limitation for a heat pump is that it must be greater than or equal to